Hey guys, welcome to the video for 7.1.3 nuclear structure. Uh, for the most part, my feeling is that you guys have probably learned this stuff already in previous years of science, so hopefully this is more of a revision for you guys, or maybe some different terminologies that we use in physics. Okay, so first off, this video is mostly a lot of definition type stuff. So first off, a nucleon is generally any particle inside of the nucleus of an atom. So it's either a proton or a neutron. So a nucleon can be either one of those. And in terms of our relative mass scale, an electron is a lot smaller in comparison to a proton and a neutron. So if proton neutrons had the mass or even the size of one unit, then an electron is 1,800 times smaller than that, okay? But in terms of charge, it still holds a full -1 charge, and a proton also holds a +1 charge in comparison. Um, so moving on, a few letters that you will see us use quite a bit. A is to represent the atomic mass number, so the total mass of the nucleus, or generally, because the electrons are um, almost weigh nothing, so it's generally the entire mass of the electron itself, or sorry, of the atom itself. Next up, the atomic or the proton number is Z, and the neutron number is N. Okay, and generally speaking, we write things in terms of, so our chemical symbol is represented by the letter X, number of nucleons A, and number of protons Z. So below we have an example of both helium and hydrogen for you, where there are 4 nucleons. So meaning there is any combination of 4 neutrons and any combination of up to 4 neutrons and protons. So, and then our other number tells us how many protons we have. So we have 2 protons. And so if we do the subtraction, 4 minus 2, that leaves us with 2 neutrons. The hydrogen atom here has 1 proton. And because there's only 1 nucleon, that means there are actually no neutrons. Another thing to keep in mind, though, is that all the elements in the periodic table have a balanced charge, which I think we will be talking about down here in isotopes. So an isotope is an atom with the same number of protons, but different number of neutrons. And it's usually that we talk about heavier elements. So usually isotopes are ones that have more neutrons, generally speaking. um, what we normally see in the periodic table here is H11, and that's generally the most common one that we at least see here on Earth, and very likely the universe as well. But that's difficult to say without analyzing other planetoids and things like that. But generally speaking, that's our assumption, which could change in the future as we discover more things. The other two here, these are isotopes of hydrogen. So they only have 1 proton. Okay, so there's only 1 proton, but there are more neutrons as indicated by the nucleon number there. Okay, so here there's 1 neutron, and here there are actually 2 neutrons in this hydrogen atom. A few more things. In terms of the fundamental forces, we have gravity, which we've talked quite a bit about in our forces unit. And we have electromagnetic force, which we will be talking about after we complete Unit 7. We have what we call the strong nuclear force, and this will probably make a little bit more sense after we complete the electromagnetic unit, but it's responsible for holding nucleons and even quarks So quarks are subatomic particles. Um, very briefly, what we're really saying is that inside of, say, a proton or inside of a neutron, there are actually little particles within a neutron like that. And those little guys are called quarks, which we'll learn a little bit more about later, but that's just a little preview of what is to come. And you may know a little bit about charges or like charges repelling each other. So if you think about that, like charges repel each other. Inside the nucleus of an atom, we have a bunch of protons and neutrons probably squeezed in together there like that, okay? Excuse me. So the protons are actually trying to repel each other with quite a strong repulsive electromagnetic force. So we need an even stronger nuclear force to hold these guys that are trying to separate each other from their electromagnetic forces. So that's why this is quite a powerful or a strong nuclear force. And it also works on a very short range, whereas electromagnetic forces can work up to an infinite range, what we would say. The weak nuclear force, which is radioactive decay, again, we'll talk more about that in the coming unit. It is also quite a short range, 10 to the power of minus 18 meters, and it acts on protons, neutrons, electrons, and this little guy V here, these are our neutrinos. Okay, so well, again, these are other subatomic particles that we will talk about more a little bit later. And okay, if we have a look at a few questions here, these are the type of questions that you're going to get. There are some questions that you will get that are related to the E&M unit, electricity magnetism. We will ignore those for now, but after we complete chapter 5, you should be able to do that. Okay, so right now, this one should be pretty easy. So we need to determine the number of protons, neutrons, and electrons of a gold atom. So there's 197 nucleons. If we subtract that, this is the number of protons already. So there's 79 protons. And so what we have left over is 197 minus 79, which is 17, 18, 118 neutrons. Okay, and this is protons, 79 protons. And electrons is always the same as the number of protons. So there are 79 protons and also 79 electrons as well. Okay, let's see here. Carbon or radiocarbon dating involves relative ratio of the number of carbon, 14 carbon 12. Carbon contains 6 protons. Write down 2 nuclide symbols. So we're really looking at C14. So this is going to be, whoops. So C14, and carbon has 6, and so that's C14, and this is C12. Okay, C12, C14. So this is the isotope of the of carbon. Okay. All right, guys. We'll see you in the next video.